Okay, good afternoon, students. In the previous lecture, we have studied the application of Gauss law for the symmetrical charge distribution, that is D due to point charge, D due to line charge, we have seen, right? Then also D due to coaxial cable, we have seen that. Then next, we have seen the application of Gauss law for asymmetrical charge distribution, right? And we have derived the expression, right? I hope you remember this, right? So the charge enclosed in the smaller volume is given by, that is the variation of the electric flux, means the charge enclosed in the smaller volume is given by the variation of the electric flux density in x direction, that is dou by dou x of dx plus dou by dou y of dy plus dou by dou z of dz into the small differential volume delta V. Delta V is equal to delta x into delta y into delta z, right? This is the charge enclosed in the smaller volume or differential volume element for asymmetrical charge distribution. We have seen, means you can observe this term, that is dou by dou x of dx, dou by dou y of dy and dou by dou z of dz. This term will give me the variation of the electric flux density in x direction, y direction and z direction at the delta V, means the small volume. As the volume shrinks to zero, it will come towards point, right? So the variation of electric flux density along x direction, y direction, z direction at a particular point, right? So that is the meaning of this, right? And delta V, it is calculated by just multiply length into breadth into height, that is delta x into delta y into delta z. Is it fine? Okay, that this we have derived in the previous class, that is the application of Gauss law for the differential volume element. This we have derived it. Okay, next I will solve few numericals based on the differential volume element in today's class. Next we'll see the concept of divergence and the numericals based on that. Okay, we'll take up the first numerical. Find an approximate value for the total charge enclosed in an incremental volume of 10 power minus 9 meter cube located at the origin if the electric flux density is given as follows, right? Okay, we will try to write down the data first, what is given. Then yes, incremental volume is delta V, it is given, that is 10 power minus 9 meter cube. Then where this incremental volume is located, it is located at the origin. So the coordinate of the origin, let me write the coordinates of the origin, right? 0 comma 0 comma 0, right? This is the value of x, y, z. Then d vector is given, right? And they have asked to calculate the approximate value of the total charge. We know the formula, q is equal to, we'll write the formula first, dou by dou x of dx plus dou by dou y of dy plus dou by dou z of dz into delta V. Is it fine? Okay, delta V is given. First we will calculate dou by dou x of dx, dy, dz, right? So here it is d vector is equal to dx into ax plus dy into ay plus dz into az. Is it fine? Okay, first we'll do one by one. So dou by dou x of dx. So dou by dou x of, what is dx here? Dx here e to the power of minus x into sine y, right? And it is a partial derivative, we have to differentiate with respect to x. So sine y is constant, so derivative of e power minus x is minus e to the power of minus x into sine y, right? And y is treated as constant. Similarly, we will try to derive dou by dou x of dy, the second term. Okay, we will find out the second term. So dou by dou y of dy here is dy into ay. Dy is minus e to the power of minus x into cos y, right? We'll differentiate it. So differentiate with respect to y means this is constant. So differentiation of cos y is minus sine y. So it will become plus sine y, right? This is fine. Second term is over. Next we'll come to the third term, dou by dou z of dz. So dou by dou z of dz, what is dz? 2z, right? 2z into dz into az, right? 2z here. So differentiate with respect to z, so I'll be getting 2. So substitute in this formula. So minus, first term is minus e to the power of minus x into sine y plus e to the power of minus x into sine y plus 2, right? So just observe the first and second term, they are same, right? So both will cancel, right? plus e to the power of minus x sin y and minus e to the power, they will cancel, and final answer I'm left out is 2. So q is equal to 2. But sorry, 1 minute. Into delta v we have left out, so write down delta v. What is delta v here? Delta v is nothing but 10 power minus 9, 10 power minus 9 coulombs. So final answer q is equal to 2 nano coulombs. I hope you understood. Right, you have substituted, but we have forgot delta v, so multiply the delta v here. Delta v is 10 power minus 9 meter cube, so q is equal to 2 nano coulombs. Right, I hope you understood this. If any doubts, you can unmute yourself and ask the doubts so that I can clarify immediately. Okay, I will go to the next numerical. In the free space, let d vector is given, and there are three parts here. Find the total electric flux passing through the rectangular surface. These are the boundaries that is given. Z is 2, x lies between 0 to 2, and y lies between 1 to 3 in the AZ direction. This is very important. We will see one by one, right? So first I will take up part A. D vector is given. Find the total electric flux, means psi. We want to find out psi passing through this rectangular surface. Boundary is given. X lies between 0 to 2 and y lies between 1 to 3 and z is 2. Right? Okay, if z is 2 means, then what is the limit of z? We will see it. Okay, means we should be from 0 to 2 only. Right, let me see it. Okay, then I want to find out the total electric flux passing through the this surface having the boundaries x lying between 0 to 2 and y lying between 1 to 3 and z equal to 2. Right, so we have the formula psi equal to q. Yes, the total amount of flux leaving the closed surface is equal to the total amount of charge enclosed by the Gaussian surface, that is equal to the closed surface integral of d dot ds. Right, okay, you can observe, find the total electric flux living in AZ direction. AZ direction means what is this ds? ds should be calculated in z direction. Be careful, right? So the differential elements in the Cartesian coordinate system are dx, dy, dz. So, and you are calculating the differential surface area along z direction. Leave this z and multiply the other two, that is dx, dy into az. Then what about d? Right? So d is given, that is dx into ax plus dy into ay, dz into az. Right? So az they have missed out here. Az should come here. Right? Okay, we have to take only dz only, right? Because if I multiply d with ds, z, so ax dot az will be 0, ay dot az will be 0, so I am left out with only the third term, dz dot az, right? So I will write it here. So surface integral is a double integral. So 16 x square y z cube, 16 x square y z cube, az dot az will be 1, so I am left with dx dy. 16 x square y z cube. Pico is there. Pico means 10 power minus 12. Don't miss it. Right? 10 power minus 12. Pico I am writing here. Pico coulomb per meter square. Right? Okay. It varies from x and y. X is varying from 0 to 2 and y is varying from 1 to 3. Right? Next we'll try to integrate. Take the constants outside with respect to x and y. Z can be taken out because we are doing with respect to x and y. So this is constant, 16 is constant, this is constant. So take the constants out. 16 into 10 power minus 12 into z cube. Take it outside, then try to integrate with respect to the other terms. So integration with respect to x I will do x cube by 3. First one, and the limits of x are from 0 to 2. Then next, integrate with respect to y. Y is y square by 2. Limits of y is from 1 to 3. Right? Okay, calculate this. So 16 into 10 power minus 12 into z. Z is how much? 2. 2 cube. Right? Then open bracket. So calculate this. 1 by 3. Upper limit minus lower limit. 1 by 3 into upper limit is 2 cube. That is 8. Right? Minus lower limit, it is 0. So I will be getting this, then into 1 by 2, open bracket, upper limit is 3, 3 square is 9, minus lower limit is 1, 1 square is 1, right? So calculate this. So I will calculate. So 16 into 8, 2 cube is 8. So I am getting it as 128, 128 into 10 power minus 12. So within the bracket I will calculate how much you will get, we will see. So 8 by 3, 8 divided by 3 into 9 minus 1 is 8, 8 by 2 is 4, right? 2 1 ja, 2 4 ja, right? It is 4. Just multiply 4 for it. So 10 point, so this one I am getting it as 10.667, right? So just multiply this with 128. So 128 into 10.667. So I'm getting it as 1365 pico. 1365 pico. 1365.376 picocoulombs. Is it right? Okay, fine. Picocoulombs. Just you can verify. It is 1365 picocoulombs, right? Okay. We'll go move to part B. Okay, what is given in part B? Let us check it. Find E vector at point P. Yes, we know the relationship between the electric flux density and the electric field intensity. D is equal to epsilon naught E, right? So we'll find out the electric field intensity at point P, right? So E at point P. So they asked to calculate E at point P. Point P is 2 minus 1 3. 2 minus 1 3. Is it fine? Okay, D is given. So first we'll find out D at point P, right? D, I will write down the D. 8xy z to the power of 4, 8xy z to the power of 4 ax, then plus 4x square z to the power of 4, 4x square z to the power of 4 ay, plus 16x square y, plus 16x square y z to the power of z cube into az. This is given, and it is pico. Pico means 10 power minus 12, right? Then substitute D at point P. Next I want to calculate D at point P. So substitute the value of x, y, z. X is 2, y is minus 1, z is 3. So substitute and calculate. So first term 8 into x is 2 and y is minus 1 and z is 3. 3 to the power of 4. 3 to the power of 4. So I am getting it as minus 1296 ax. Next second term we'll see 4 into x square. 2 square is 4 into z to the power of 4. 3 to the power of 4. So we are getting it as once again 1296, same thing, 1296 ay, plus we'll see the third term 16 into x square, that is 2 square is 4, into y, y is minus 1, into z cube, that is 3 cube. So I'm getting it as minus 1728 az pico, 10 power minus 12 coulomb per meter square. Then calculate E. We know the relationship between D and E, right? So which implies E is equal to D divided by epsilon naught. So D, we have calculated D at point P, right? So E, I want E at point P, right? Divided by epsilon naught 8.854 into 10 power minus 12. Okay, we'll see what we will get. E vector at point P. Okay, 10 power minus 12 and this 10 power minus 12, right? D at point P is having 10 power minus 12. It will get cancelled. So just I will divide it by 8.854. This 10 power minus 12 and this 10 power, they will get cancelled. So just I will divide and write 1296 divided by 8.854. So I am getting it as 146. So sign minus is there, 146.374 ax. Then it is also 1296 divided by same thing I will get. It is 146.374 ay. Then third one minus 1728 divided by 8.854. So I'm getting it as 195.166 az. So what is the unit of electric field? It is volt per meter. Just cross verify. Right, minus 146 plus 146 minus 195, right? We're getting the same answer, volt per meter. E at point P is over. We'll move to part C. Part C, what they asked, find an approximate value for the total charge contained in an incremental sphere located at P of 2 minus 1 3 and having a volume of 10 power minus 12 meter cube. We'll write down the data. The volume of the incremental sphere, it is 10 power minus 12. We'll write it. So delta V is equal to 10 power minus 12 meter cube. Right? 10 power minus 12 meter cube. Then where it is located at point P of 2 minus 1 3, and it is asked to calculate the approximate value of the total charge Q. So we know the application of Gauss law for the differential volume element. We know that formula, right? Q is equal to the variation of flux dou by dou x in x direction and variation of flux in y direction dou by dou y of dy, and variation of flux in z direction dou by dou z of dz multiplied by delta V. Right? Okay. D is given. This we have. So at point P they have asked, right? Already we have substituted at point P. What is D at point P? Already we have here. But before, we will not take this D at point P, because if I take the derivative with respect to x, this will be constant, it will be 0. So first you take the general electric flux density vector, D vector, then differentiate it, then you calculate, right? So one by one you will calculate. So first I will calculate this, next second dou by dou y of dy, then third dou by dou z of dz, right? And this is dx into ax plus dy into ay plus dz into az, right? Pico is there, so take care of this. So we'll differentiate. So dou by dou x of dx. So dou by dou x of dx. Already we have okay. No, we have not yet calculated. So dx is what? 8xy z to the power of 4. 8xy z to the power of 4. 8xy z to the power of 4. Differentiate, partial differentiation with respect to x. So 8y z to the power of 4. I am getting it as 8y z to the power of 4. Right? Then don't forget this pico, right? We'll take care of this pico at the end. So dou by dou x of dx is 8y z to the power of 4. Next, similarly, we'll do the second differentiation, dou by dou y of dy. Dou by dou y of dy is how much? 4x square z to the power of 4. 4x square z to the power of 4. So differentiate this with respect to y. Since all are constant, so it will be 0. Second term is 0. Then coming to the third term, dou by dou z of dz. So dou by dou z of, what is dz? That is 16x square yz cube. 16x square yz cube. 16x square yz cube. So we will try to differentiate with respect to z. 16x square y is constant. So differentiation with respect to z, z cube is 3z square. So 16 into 3. Right? 16 into 3, it is 48. 48 x square y and 3z square, right? 3 is already taken care. 3z square. So 10 power minus pico minus 12 I should not leave. So 10 power minus 12 will come here. So q is equal to. So first term is how much? What do we got? 8y z to the power of 4. 8y z to the power of 4 plus second term is 0. Second term is 0. Third term, it is 48 x square yz square. 48 x square y z square. Then 10 power minus 12, we will take it. Then what is delta V? The small volume, it is once again 10 power minus 12. Right? This 10 power minus 12, it is of D, electric flux density, right? We have to take care about that also. So substitute the value of P. P is 2 minus 1 3. P is 2 minus 1 3. So x, y, z, substitute and calculate. Okay. So 8 into y is how much? Minus 1. The z is 3. 3 to the power of 4. So I am getting this as minus 648. Then I will, this is 0. I will take the third term. 48 into x square, that is 4, 2 square is 4, into y is minus 1, into z is 3, 3 square, that is 9. So I am getting it as minus 1728, minus 1728. So into 10 power minus 12 plus 12, right, 24. So q is equal to, we'll calculate this, minus 648 minus 1728. So I'm getting it as minus 2376 into 10 power minus 24 coulombs. So cross verify. So here minus 2.38 into 10 power minus 21, minus 2.376. Yes, instead of 10 power minus 24, we can express in terms of 10 power minus 21 as per this answer, right? We will express 10 power minus 21 coulombs, right? Minus 21 means 10 power minus 3. Take 3 digits below, right? Ahead of this. So minus 2.376. So minus 2.38, right? One and the same. I hope you understood this. If any doubts are there, you can unmute yourself so that I can clarify the doubt immediately, right? Right, we'll move to the next topic. Right, the next topic is divergence. Okay, already we have seen. Okay, let me wait for the siren to stop. I'll continue. Okay, as discussed in the previous lecture, the charge enclosed in the smaller volume. We have applied the Gauss law for the differential volume element, and we got this expression, that is charge enclosed in the smaller volume delta V is equal to Q, and that is equal to closed surface integral of d dot ds, and it is equal to variation of the electric flux density in x direction, y direction, z direction over the smaller volume delta V. This expression we already know it. And as I already told, this concept will lead to the concept of divergence, means the spreading nature of the field, the divergence, right? So what is divergence and what is the mathematical form of divergence, right? We'll see here. Okay, we know this equation. We can rewrite this equation, keep this on LHS as it is, then divide it, right? This is on LHS. Just divide this by delta V, this first term, and second term here, divide Q by delta V. The same thing has been done here, right? Then allow the volume to shrink towards zero, means we are considering the smaller differential volume. It is as good as a point, because as delta V shrinks to zero, while the volume shrinks to zero, it is giving me the point effect. At the point, what is the nature of the variation of the field, right? At the point. So apply the limit. For this, limit delta V tending towards zero, the closed surface integral of d dot ds divided by delta V, right? For this, apply the limit for this, limit delta V tending towards zero, Q by delta V. So this charge per unit volume is nothing but the volume charge density rho V, right? This I can replace by rho V. But this we'll see it in the later discussion. So right now we are interested with this term, right? The limit delta V tending towards closed surface integral of d dot ds by delta V. Only this much, right? We'll concentrate on this and we'll try to explain the concept of divergence that has been mentioned here, right? In equation 2. This equation 1 will take the discussion later. Okay, same thing. Okay, we'll concentrate on this. It is not mandatory that we can apply divergence only for electric flux density. We can apply the we can apply the divergence for the velocity, temperature gradient or force or any vector field, right? We can apply, please keep in the mind, we can apply the divergence for any of the vector field. That vector can be either the electric flux density or velocity or temperature gradient or force or any other vector field. So instead of D, we can replace by some other vector quantity A, vector A. Let me take it vector A. So by using this equation, I can write dou by dou x of ax, ay and az. It is equal to limit delta V tending towards closed surface integral of a dot ds into delta V. We will take this general equation for defining the divergence, right? Okay, in the next slide I have taken S. This entire quantity here, this entire quantity I will call it as divergence. Divergence of A. Divergence of vector A, right? Or else simply I can write divergence of vector A, this entire quantity within the bracket. So we will make use of this notation. The divergence of vector A is equal to limit delta V tending towards zero, closed surface integral of A dot ds by delta V. Now we will try to define the divergence, right? So the divergence of the vector flux density, it can be any vector, I told already. It can be electric flux density, it can be velocity, it can be temperature, it can be force, right? So we'll try to define it. The divergence of the vector flux density A is nothing but, right? Here we are defining the LHS first. The divergence of the vector flux density A is nothing but the outflow of flux. This one, the outflow of flux from the small closed surface. The outflow of flux from the small closed surface. We are referring to this, the outflow of flux from a small closed surface per unit volume. As the volume shrinks to zero limit, right? So now we will define it without looking at this definition, right? So the divergence of, instead of A, you can take the electric flux density and define it, no problem, right? So the divergence of the electric flux density is nothing but the outflow of the electric flux over the closed surface per unit volume as the volume shrinks to zero, right? Means this divergence, the physical significance of divergence is, it will tell the spreading nature of that particular vector field. So in a region at a particular point, if I have a particular point, right, how the field will vary in different directions, it will tell the spreading nature of the field, right? If it is force, it will tell, yes, the spreading nature of the force or velocity or temperature gradient in different directions, right? So we will take the two examples to understand the divergence here, right? So the divergence of velocity of water in a bathtub after the drain has been opened. Okay, we'll take this scenario. So this is the bathtub, right? Then there is a outlet for it, there is a drain, right? Okay, and there is a wall. I can either open or close it, right? Okay, fine. And it is filled with water. This is the bathtub. Okay, in this scenario, what we have done, we are draining the water out, means open the wall. We are opening the wall and the water is coming out of this drain or pipe, right? Okay, then I want to define divergence of the velocity of the water at each and every point within the water. I will consider point A here within the water. Don't take outside the water. We take the point within the water, well within the water. Then I will consider another point P, well within the water, right? I can consider the point anywhere within the water, right? So let me consider point A here. Here, whenever the valve is opened, the water tries to rush out of this wall or drain, right? It will rush out. Then if I consider at this point A, the very small point or very small volume is considered at point A, what will happen? The water is incompressible. The total amount of water entering this point A or smaller volume is equal to the total amount of water leaving this point A or smaller volume. Means the divergence of the velocity of the water at point A is zero, because at this point A, what is happening? The amount of water entering is equal to the total amount of water leaving, right? Hence, if I consider the velocity of the water at the before point A and after point A, the divergence of velocity of water is zero, because the total amount of water rushing or the velocity with which it travels to point A is almost same, right? So the divergence of the velocity of the water at point A is zero. Similarly, if I take at point B, same, the divergence of the velocity of the water at point B is also zero. Is it fine? Okay, next. Okay, just I will observe the time. It's already 12:36. Okay, let me take till 1. Okay, another 10 minutes I'll take. Next. Next, second example. The divergence of velocity of the air in a tube which has just been punctured by a nail. Yes, I have the tube filled with air. Let me assume this is the tube. It should be closed, but I have taken only half tube, right? It is filled with air everywhere and it is punctured, right? There is a hole here. The air will try to rush out in all the directions through this hole. Then I want to find out what is the velocity of air. That means at each and every point within the tube. Means I will consider point A here. I can consider the point A or any point anywhere within the tube here. Let me consider point B here. What will happen? Observe here. As I approach nearer to the hole, the velocity of the air will increase. Means it means the air will rush with higher velocity at the near the hole. So point A is here. So at this end, which is near to the hole, the velocity of the air here towards this will be more as compared to the velocity of the air entering the point A. Means the velocity at the point where the velocity of the air entering point A is less than the velocity of the air leaving the point A. Means at what is the divergence at point A? It is positive, means it is near to the hole, it is rushing out, right? The velocity of the air is more towards the, means everywhere it is living in all the directions, right? The spreading nature of the air with different velocity, right? So this divergence is positive, means divergence of velocity is greater than 0. It is not 0 here as in the previous case, it is greater than 0, means divergence is positive. How can we decide that the divergence is positive, negative or 0? That we will take up, we will discuss the scenario. So we will say that the divergence is positive or negative or 0. You can observe at point P, the field, the field may be, it may be force or it may be velocity or it may be electric flux density or whatever it is, right? So at point P, you can observe, let me take the electric flux density only. The flux lines are living everywhere in all the directions. If the parameter is varying or if it is moving away from the point P, if the field is varying or moving away from point P, then in such case we say that the divergence is positive, right? The divergence is positive, right? This is the source of that particular field, source of the field at point P. This is the source, right? Then in the second case, you can tell it this is the source. Whenever we have the source, the divergence is positive. Whenever we have the sink, right, the divergence is negative. The divergence is negative. You can observe here at point P, the field lines are entering here, right, in all the directions. Hence the divergence is negative. So divergence is negative for the sink, divergence is positive for the source. And you can observe the third case. So at point P, the amount of field lines entering the point P is equal to the amount of field lines leaving the point P, means, right? So the divergence at point P is 0 because the total amount of field lines entering is equal to the total amount of field lines leaving point P. Hence the divergence is 0 in the third case, right? So for source, divergence is positive. For sink, the divergence is negative. And source and sink both, right? There is a source also here at this and on this sink. Source and sorry, this is sink and this is source, right? So hence the divergence at this point P is 0. And please note, the divergence of a vector quantity is always a scalar. If I find out the divergence of a vector, it is always a scalar quantity. Means divergence of vector A, what it will give me, it will give me a scalar quantity if I calculate. Then how to calculate the divergence we'll see, and the divergence in different coordinate systems, right? Okay. Already we know the divergence of D vector in Cartesian system or rectangular coordinate system, right? So the variation of flux in x direction, y direction, and z direction, dou by dou x of dx plus dou by dou y of dy plus dou by dou z of dz. This is in Cartesian system. Similarly, the variation can be well explained in other coordinate systems also, that is cylindrical and spherical. We can observe the divergence formula in cylindrical coordinate system. So how to remember this, I'll tell you, right? If you are having very good memory power, you can remember it directly, or else we have the trick how to remember it. I'll tell you that also, right? Just have a look at it. So this is the divergence of D vector and the spreading nature of the field in rho direction, phi direction, z direction. If I consider the cylindrical coordinate system, then if I consider the spherical coordinate system, the spreading nature of the field in radial direction, theta direction and phi direction. This is the formula, right? Okay, just have a look at the formula and try to remember it, or else I will tell you how to remember it, right? Okay, this is the general, we will try to define the general coordinate system, that is general curvilinear coordinates u, v, w. These are the general curvilinear coordinates, right? If it is in Cartesian, this u, v, w can be replaced by x, y, z in Cartesian. In cylindrical, we can replace this u, v, w by rho, phi, z. In spherical, we can replace this by r, theta and phi. The same thing has been written here, right? U, that is x, y, z in Cartesian, rho, phi, z in cylindrical, and r, theta, phi in spherical, right? The same thing I have written here, right? This is in rectangular coordinate system, cylindrical coordinate system and spherical coordinate system, right? Okay, these are the variables. Then what about the scale factors? In the second line I have written h1, h2, h3. This we call it as scale factors, right? So in Cartesian, the scale factors are h1, h2, h3. h1, h2, h3. These are the scale factors. So in Cartesian, the scale factors are 1, 1, 1. I'll tell you. This is in rectangular coordinate system. If it is cylindrical coordinate system, the scale factors are 1, rho 1. If it is spherical coordinate system, the scale factors are 1, r sine theta. Right? Okay. If I want, okay, and differential elements, that is, we can write it as du, dv, dw. And in rectangular, it is dx, dy, dz. In spherical, it is d rho, d phi, dz. And in this is in cylindrical. In spherical, it is dr, d theta, d phi. And scale factors I have written exactly below this. And if it is asked to write down the differential elements in rectangular coordinate system, just multiply the corresponding scale factors. This is h1, h2, h3. Just multiply h1 into dx, so I will get dx. h2 into dy, it is 1 into dy, I will get dy. 1 into dz, right? This is the differential elements in rectangular coordinate system. Then if I come to the cylindrical coordinate system, just multiply the corresponding scale factors. 1 into d rho, I will get d rho. So rho into d phi, then 1 into dz, right? This is the differential elements in cylindrical coordinate system. In spherical coordinate, just multiply 1 into dr. So r d theta, then multiply the third, r sine theta into d phi, r sine theta into d phi. So this is the differential elements in spherical coordinate system. I hope you understood what are the variables and what are the scale factors. H1, H2, H3 are the scale factors. U, V, W are the variables, right? In different coordinate system. Then how to write down the divergence of D vector in different coordinate system? Just if you remember this summation, you can easily write down the divergence formula in all the three coordinate system. So the divergence of D vector is equal to 1 by H1, H2, H3 summation of dou by dou u of H2, H3 du. Just I will show you how to write down the formula for in one of the system, right? Okay, in Cartesian, it is fine, comfortable, no problem. Just I will show you how to write in spherical coordinates. How will get this, right? So I will, with the help of this, divergence of D vector is equal to, so I will write it here only. Divergence of D vector is equal to 1 by H1, H2, H3 into summation of dou by dou u of H2, H3 into du. Okay, we will expand this first. So 1 by H1, H2, H3 into dou by dou u of first term is H2, H3 into du. So I'll expand this summation dou by dou v. After u, next comes v. H2, H3, 2, 3 is over, right? Next 3, 1, H3, H1. H3, H1 into dv plus dou by dou w of 2, 3 is over, 3, 1 is over. Next 1, 2, H1, H2, H1, H in the cyclic order. First we have started with 2, 3, next 3, 1, 1, 2, right? H1, H2 into dw. So we'll substitute the scale factors and the variables here so that we can write the formula here, right? So I'm showing you how to write the divergence of D vector in spherical coordinate system, right? Divergence of D vector is equal to 1 by, what is H1, H2, H3 in spherical coordinate system? 1 r sine theta, right? This is H1, this is H2, this is H3 in spherical coordinate system. 1 r sine theta. So just multiply 1 by H1 into H2 into H3. 1 by r square sine theta. 1 by r square sine theta. Right? This is over. Next, dou by dou u means dou by dou r. We will replace u by the first variable r. Then H2 into H3. Just multiply H2 r square sine theta. R square sine theta into du. Du is nothing but dr, right? Plus dou by dou v. Next, uv means our next coordinate is theta. Dou by dou theta of h3 into h1. h3 is r sine theta, right? h1 is 1. R sine theta into d theta. dv is nothing but d theta plus dou by dou w of h1 into h2. Multiply 1 into r and d r theta phi, sorry, r theta dou by dou phi of r d phi. Just compare this formula and this formula, just multiply 1 by r sin theta. So finally I will get 1 by r square. Just multiply this first with the first term. So with respect to r means sin theta can be taken out. So you multiply sin theta will get cancelled. So I will be getting 1 by r square dou by dou r of r square into dr. Right? First term over. Next multiply this 1 by r square sin theta with the second term. So with respect to theta, r is taken out. So r will get cancelled 1 by r sin theta. So I am getting 1 by r sin theta dou by dou theta of sin theta into d theta. Second term is over, right? Then coming to the third term, multiply this. So r can be taken out. Once again 1 by r sin theta will come here. Then next dou by dou phi of d phi. I hope you got how to write the formula in all the three different coordinate system just by remembering this summation, right? Okay. I'll stop the today's lecture. I'll stop recording.